Hello, I welcome you to lecture 24 of 3N03. We'll start our discussions of the bipolar junction transistors. And in this lecture, I will discuss the structure of bipolar junction transistor, the operating regions, and we'll start to talk about the biasing, a very simple biasing equation that we have to observe when we solve for the different currents and voltages. The bipolar junction transistor is really three layers of semiconductor material. This is an emitter and then a collector, and in between the emitter and the collector there is a base. Each one of them, when they fabricate these structures, each one of them will have its own metallization. This is how you connect the base, connect to the emitter, and this is the collector. The emitter is usually highly doped. It's maybe if this is an NPN transistor, so this would be an N-type material, this is a P-type material, this is an N-type material. The emitter is heavily doped more than the collector, and the base is very thin and lightly doped layer. Here it's not really drawn to scale, but the base usually is way thinner than the emitter and the collector, and is lightly doped, and the emitter really is the highest dope area here. And for an N-type, for an NPN transistor, this would be N-type, this would be B-type, this would be N-type. Okay, and we have current here in this case. For an NPN transistor, current will be flowing from the collector to the emitter. So current will be flowing this way, and you get as well some current being added from the base, and the current and the sum of the current from the collector and the current from the base will give you the emitter current. So structure-wise, these are two layers of N-type material, and between them there is a layer of B-type material. This for an NPN B-jet. For a PNB B-jet, it's a P-type material and another B-type material, and between them there is an N-type material. For circuit symbol, this is a circuit symbol of an NPN transistor. This is the base, this is a collector, this is the emitter, and this arrow here shows the direction of flow of the current. So for this one, and when you do circuit analysis, current will expect to flow this way. This is from the current to the collector to the emitter, and current will expect also to flow from the base to the emitter. This is a little bit different from what we learned with FETs, because in FETs we had no current flowing into the gate. While here for the base we have some current, not really a big current, it's a weak current, but there is some current flowing through the base, and the emitter current is equal to the collector current plus the base current. For a BNB transistor, the arrow shows the direction of flow of the current. So the current usually flows this way. Okay, the current flows this way, and for the base, the current really is flowing out from the it would be flowing this way. Okay, so in that case, we can simply say that the emitter current is equal to the collector current plus the base current, and we'll get more into the details of that. The bipolar junction transistor is named as bipolar junction transistor because we have two types of carriers, electrons and holes, and we can they both really interact together to create the functionality of this transistor. Okay, biasing the transistor, as we have seen before for the FET transistors, we have to apply some voltage between over there was the gate and the source, here between the base and the emitter, and some voltage between the collector and the emitter. When you apply some voltage between the collector and the emitter, this source here is trying to push current from the collector through the emitter, and the value of this current going from here to here will depend on the value of the current flowing into the base. Okay, so the same thing is also happening for a BNB transistor. So first for NPN, this is the direction of the collector current. This is I collector, it's flowing in. This is the direction of the base current. Okay, it's a weaker current, much weaker current, and this is the emitter current. This is the emitter. Okay, and you can see the arrow direction indicates the direction of the emitter current. For a BNB, you can see we use different polarity here. So we're trying to make the emitter more positive than the base, and we're trying to make the emitter more positive than the collector as well. So this one makes the emitter more positive than the collector, while this one makes the emitter more positive than the base. And the current in this case will be flowing this way. This is the emitter current, it's flowing into the emitter. This is the collector current flowing out, and this is the base current. Okay, and in that case the same equation holds, that I emitter is equal to I collector plus I base. This equation holds for both of them. Now, there are different modes of operations of these transistors. The one that I'm showing you here, this is called forward active region, or called the active region. If I say active region or active mode only, I mean it's forward active mode. So what's happening here, you try to make for NPN transistor, you make the base more positive than the emitter, so this junction is forward biased, so this voltage here will be around 0.7. You try to make the collector more positive than the emitter, and because these are the same type of material, this is not a junction, so the voltage here can be any value really. And so this try to push current here, and the value of the current flowing will depend on the bias being applied to the base. And the same thing is happening here. This emitter has a higher potential than the collector because of the polarity of the source. So the source tries to push current this direction. Okay, and the value of this current will depend really on the base current. But here notice where the emitter is more positive than the base, and the emitter is more positive than the collector. For BNB is the reverse of the NBN. Okay, from our previous studies in BN junctions, we know that when you put a B-type material, N-type material, this creates a depletion region on contact. In few microseconds maybe this will create a depletion region, and then you end up with this sort of barrier. So this is a B-type material, this is an N-type material. You can see the electrons in the conduction band of the N-type material. Their energy is not sufficient for them to be able to cross into the conduction band of the base of the B-type material. So this is why they cannot really, in steady state, they cannot cross from here to here and create a current. So this is the emitter, this is the base. The same thing is happening between the junction between the N-type material of the collector and the B-type material of the base. When you put them together, there will be some initial movement from electrons and so on, and this creates a depletion region, and then this region will be really depleted of high energy electrons. So all the electrons that will remain do not have enough energy to be able to cross the conduction band in the base region. This is before any biasing. Okay, so now when we apply biasing to the transistor, we apply certain voltage between the base and the emitter, and certain voltage between the base and the collector. The first case, which is the most important case for us, is when we make the junction between the base and the emitter forward biased, and the junction between the base and the collector reverse biased. This is called the forward active region, or the active region, or the active mode, and this is the one that we use usually for amplification, when we use the transistor as an amplifier. So if I now apply, if I get a battery here and then I connect it this way. Let me just try to draw it for you here. If I connect the battery this way, so I'm now making the base. I'm forward biasing the junction. This is B-type, connect to the positive side of the battery, N-type the negative side. This will result, as we explained earlier for BN junction, in raising the energy levels of the conduction band in the N-type material, and lowering the energy level in the conduction band of the B-type material. Now, if we reverse bias this one, not forward bias, if we reverse bias this one, then we connect really a battery that looks something like this. So we are making the N-type material more positive than the B-type material. Then we'll actually push this energy level even lower. We'll make the conduction band of the collector go down, of the N-type material, while the conduction band of the B-type go up. So in that case, if you put all this together, this is what we'll end up having as shown in the next slide. This is what we effectively get if we do forward region or forward active region biasing. We forward bias the emitter base junction and reverse bias the collector base junction. So now the conduction electrons in the emitter side will have more energy. They can now flow very easily into the base, and also holes in the base can also flow in the valence band through to the N-type material. So you get electron current flowing this way. Okay, actually this is the flow of electrons. It's not the direction of the current. The current actually flowing the other way. Okay, but this is the direction of the flow of the electrons. This is the direction of flow of the holes. Now for this side, these electrons really cannot cross this way. They cannot climb up this hill. Remember, this side was reverse biased. But the good thing is, if the base is sufficiently thin, then the electrons that are able to cross from here to here, they will have enough energy, and then they find it's very easy for them to go to the conduction band, the conductor, in the collector side. So this means that what's called they roll down the energy hills, because the energy is way higher than the energy required for them to be in the conduction band of the collector. So this results in a flow of electrons from the emitter to the collector, or a flow of current from the collector to the emitter. So this is the collector current, and this is the emitter current. And of course we have the base current as well. This is an actual direction of the base current, because this is a flow of holes. So now we have three types of currents. An emitter current, simply electrons in the conduction region of the emitter have enough energy to cross into the conduction region of the base. Base current, we have holes in the valence band, okay? They are able to cross as well to the other side, and there is some combination happening between them. We have the collector. Whatever electrons that did not recombine here with the holes will be able to roll down the hill, this energy hill. Really, it's an energy hill. They have way higher energy than the one required for them to be in the conduction band of the collector, and this means they will be able to have a current here. So this flow of electrons is equivalent to current flowing in this direction here. So this is the collector current, this is the base current, and this is the emitter current. And as I explained earlier, I collector is plus I base is equal to I emitter. Okay, so this is called active region of operation, and this is the most important one we use for BJT transistors to use them as amplifiers. Okay, as we agreed, we consider the whole transistor as one big node, and for NPN transistor, I collector plus I base equal to I emitter, and for a BNB transistor, I collector plus I base equal to I emitter. Again, we consider the whole transistor as one big node. Usually, I base, the base current is very small, as we agreed. The base is very thin, slightly doped. Then the base current is usually in the microampere, very little, while the current, the collector and the emitter currents are way bigger. And usually, there is an approximation that you can say that most of the emitter current will flow in the collector. You can do this approximation as well. Now, in the forward active region, the relationship between the collector and the base is given by a parameter of proportionality called the DC current gain. So this ratio here, this expression is valid only for the case of the forward active region, or for the active mode of operation. Okay, so this is what's called beta DC, is a DC current, and I will show you when we talk about the characteristics that in this region of operation, IB and the IC are not independent. They are related by a certain ratio. It's a function of the transistor, and this function is called the beta DC, and takes a value between 2 to 200. And the higher the value of this one, the higher the gain. So what is happening? You apply very little current at the base, and this results in a way bigger current at the collector. So if you have a small variation of this current at the base, will result in way bigger variation of the voltage at the collector. And this is how you get amplification, because the ratio between this change to this change is 200. Now there is another parameter which is derived from beta. It's called alpha DC. Alpha DC is the ratio between I collector to I emitter. And as I mentioned to you, the collector and the emitter, they have almost the same order of magnitude, and is way higher than the value of the base current. So I collector to I emitter is equal to I collector over I collector plus I base. Remember, the emitter current is the collector current plus the base current. We can divide the numerator and denominator by I base. You end up that alpha is equal to beta over beta plus 1. Beta is a number, big number, 100, 200, and so on. So this B alpha DC is usually very close to 1. You can see it ranges between 0.95 to 0.99 for most practical transistors. Even though in most of the examples we're going to be considering in this course, we assume that beta is a constant. The ratio between the collector current and the base current in the forward active region is constant. This is not really the case. If you try to plot beta for different current values, you'll see as the current increases for the same temperature, the beta will increase, the value of beta will increase, and then will start to decrease. So it's not really that constant, okay? It shows some fluctuation. And of course, beta also increases with increasing the temperature. So the higher the temperature, the higher the value of the gain. And sometimes they use this characteristic to build devices that depend on temperature, things that can make you measure the temperature, because if you have beta changing with temperature, then you can detect the value of the temperature maybe from a measured voltage or from a certain current flowing in your circuit. So for most of the examples we're going to be seeing, we usually assume that beta to be a constant, 100, 200, 150, and so on. But in reality and in data sheets given by manufacturers, usually beta will have will show some dependence on the current and on the temperature. If you open a data sheet of a certain transistor, like this one here, 2N3N03, you will see they took a parameter called HFE. HFE is another name of beta DC, of the beta, and they show you the range for which this one will change, maybe with the temperature and so on. You can get all type of curves from the manufacturer. So they fix they simply fix the current IC, and then they allow other parameters to change, and then they'll show you how the beta is going to be affected by that. So data sheets give usually very detailed information on the change for these parameters. Okay, when we get to analyze circuits containing transistors, there are certain rules we have to observe. As we have seen for the case of FETs, we say that there is no current flowing into the gate. There is the voltage VGS will have to be greater than certain threshold in order for the transistor to be on. The same thing will happen here. For this is a transistor here. We are trying to forward bias the base relative to the emitter. You can see the polarity of this battery here. We are trying to forward bias the collector relative to the base as well. We're applying very high voltage between the collector and the emitter. So we're trying to force current to go this way. So for this case, it's very safe to say, because of the bias of the biasing here of this battery, we can simply say that this junction is forward biased. And when it's forward biased, we can assume that VBE is approximately equal to 0.7 volts. Of course, if this one is as much smaller than 0.7, then this will not be forward biased, and the transistor will be off. In this circuit, we have two loops. Actually, more than two loops, but the two main loops are this loop here and this loop here. This is a base loop, and this is a collector loop. For the base loop, the equation governing it is that VBB is equal to IBRB plus 0.7 plus I emitter multiplied by RE. So let it be this again. VBB is equal to IBRB plus 0.7 plus I emitter multiplied by RE. Okay? So for using this equation, I should be able to derive an expression for IB. Why? Because I emitter is approximately equal to I collector, and I collector is simply equal to beta multiplied by IB. Or I can simply replace the I emitter by I collector plus I base, and then I can simply replace I collector by beta IB. Both of them should give us pretty much the same answer. If we keep this one here, this is the one that we have. We collect all the terms containing IB. I'm able to determine the value of IB. So you can see if you change VBB, if VBB goes through some fluctuations, sinusoidal fluctuations, this will result in all sinusoidal fluctuations in IB because of this expression. So I now know what is the value of IB. Now, if we are in the forward region of operation, or forward active region of operation, or the active mode, then the relationship between the collector current and the base current is given by the DC current gain, which is beta DC. This number should be given to us. It's a function of the type of the transistor. Now, if I know I collector and I know I base, then I know I emitter. I emitter is equal to I base plus I collector. Now we are able to solve for the other region, for the other loop here. So we have VCC is equal to ICRC plus VCE plus IE multiplied by RE. I know all this right now. Because I already have IB. If I know IB, then I know IC. If I know IB and IC, then I know IE, because IE is the sum of IB plus IC. Then I can get VCE. Usually, VCE should be greater than 0.7, because what's happening, the base is higher than the emitter by 0.7. So in order to make this the collector base junction reverse biased, you have to make the voltage of the collector higher than the voltage, higher than the emitter voltage by at least 0.7 to make this junction here reverse biased. Okay, so the collector voltage, because it's an N type, should be higher than the base voltage. VBE is 0.7, then VCE must be greater than 0.7 to be in the forward active region, to have the collector base junction reverse biased. Okay, let's take a look at an example. Determine IB, IC, IE, VBE, VCE, and VCB for the shown circuit. Take beta DC equal to 150. It's a very simple example. One transistor here. We have one biasing directly applied to the base, another biasing applied to the collector. We simply apply the rules that we learned. We first can get the base current. The base current, if of course this 5 volts trying to forward bias the base emitter junction, so this will be 0.7. Then the current flowing in is 5 minus 0.7 over 10K. I have IB. I will assume the forward active region of operation. So if this is IB, then this one will be I collector will be beta IB. Then I know I collector. And then if I know I collector, I can double check that I'm indeed in the forward active region. The collector emitter voltage should be higher, equal or higher than 0.7, because if this is 0.7, this must be higher than 0.7 for the collector to have a higher voltage than the base, because the collector base junction has to be reverse biased in order to be in the forward active region. If this is not satisfied, then you are not in the forward active region, and the assumption that alpha, that the collector current is equal to beta IB is not valid. Okay, now let's see the steps, detailed steps in the next slide. So these are, I redraw the circuit, and then I show here the direction of IB, IC, and IE. This is VBE, this is VCE, and this is VCB. We know that this battery here is trying to forward bias the base emitter junction. Then this will be 0.7, like we dealt with diodes before. And then the current flowing here will be 5 minus 0.7 divided by 10K. This will give us a relatively small current, 0.43 milliampere. Assuming forward active region of operation, assuming this, then I collector is equal to beta IB. Then I take this number, multiply by 150, and we get good 64.5 milliampere. This is significant current flowing here. Remember that I emitter is equal to I collector plus I base. I can get the I emitter as well. Now we have to verify that indeed we are in the forward active region. The collector emitter voltage must be at least 0.7 for the collector to have higher than or equal voltage to the base. Otherwise, this assumption that I collector is equal to beta I base is not valid. So we go back and then analyze the outer loop. I simply did not draw the other loop here. I assumed we're already done with that. We know the collector current. We already calculated this. Now let's calculate VCE. VCE is equal to VCC. Sorry, maybe we should do the other way around. VCC is equal to I collector multiplied by 100 ohm plus VCE. So VCC is equal to I collector multiplied by 100 ohm plus VCE. Or I can get VCE is equal to VCC, which is 10 volts, minus 64.5 milliampere multiplied by 0.1K. So I replace this 100 ohm by 0.1K. This one by this one will give us 6.45. Out of 10, you get 3.55. So VCE 3.55 volts. This means that the collector voltage is higher than the base voltage. So indeed, the collector base junction is reverse biased, and our assumption is valid. If this number was less than 0.7, then our assumption that we are in the active region is not valid, and we have to repeat the problem assuming other regions of operation, as I'm going to show you very soon. Now the last thing we know, we need VCB. VCB, the collector to base voltage, is by definition V collector minus V base, or we can simply write it as V collector minus V emitter minus V base minus V emitter, because if you expand that, V emitter will cancel out. You end up V collector minus V base. So if you put all this together, this is VCE, we already calculated that. This is VBE is equal to 0.7. So VCB will be 3.55 minus 0.7 will be equal to 2.85 volts. So now we know indeed that we are in the forward active region Base emitter junction is forward biased. Collector base junction is reverse biased. There are actually 4 regions of operation for the transistor, or for the bipolar junction transistor. The first one we have shown here. When you forward bias this junction, you reverse bias this junction, then you are moving the energy level of the N-type material of the emitter, reducing the energy level of the N-type material of the collector, allowing electrons to flow through the base, the thin base, and then roll down the energy level to the collector, or allowing current to flow this way and then that way. This is the active mode of operation, and this is the one we're using for amplification. The reverse mode of operation is simply to use the emitter as a collector and the collector as an emitter. So you can see here, I'm forward biasing the collector to base junction, and I'm reverse biasing the emitter base junction. The only drawback of this one is that the emitter is not as a collector is not as highly doped as the emitter, and then the gain will be the beta will be lower. Beta will not be the same. We use this one for amplifiers. This one is rarely used. This mode is rarely used because of the asymmetry in the doping of the bipolar junction transistor. The saturation mode, where we allow them both to be forward biased. So you can see we forward biased the BN junction, the emitter base junction. So you see all the energy levels are fine, electrons can flow. We forward biased as well the collector base junction. So electrons can flow very easily here and here. But when you do this, the drop between the collector and the emitter will be very low. It's actually going to be less than 0.7. So in that case, the transistor really represents, as you'll see, like a resistor. It acts like a resistor. This is what we call the ohmic region, or the linear region for FETs. But it's called there the saturation region. So you have to be careful. What we call saturation region FETs is what we call here the active mode of operation, and what we call here saturation mode for BJETs is effectively the linear mode or the ohmic mode of operation for the FETs. The last, and this one is fine. This one we use it when you use the transistor as an on switch. When you try to make the transistor represents very little resistance, very little voltage drop. This is the mode you should be using. The fourth mode is a cutoff mode. When you reverse bias both junctions, you are making it impossible for electrons to flow from here to here or from here to here. In that case, no current is flowing, the transistor is off. We use this mode as well. We use these two modes actually when we use the transistor as a switch. So when the transistor is on, it represents very low resistance, and this is the mode we use, the saturation mode. When the transistor is off, it represents an open switch. For amplification, we use the active mode of operation. Similar to the FET case, we're able to draw IDS versus VDS. Here we draw I collector versus VCE, because the collector corresponds to the drain, the emitter corresponds to the source, and the base corresponds to the gate. So you can see if you try to fix the base current, so for a certain base current, it changes VCE from 0 up to very high value. You'll see in the beginning when the VCE is less than 0.7, we have a linear region of operation. The current changes linearly with the VCE, but the drop is very small. When you reach 0.7, the current suddenly becomes almost flat. It's not exactly horizontal. There is some slope, but and the problem was going to be calculating, we usually ignore this slope. We assume it's a horizontal slope as we did for BJETs. So here, this is the active region of operation. The base emitter junction is forward biased. The collector base junction is reverse biased. And here the current does not depend on the VCE. It depends only on the base current. This is exactly what we had for FETs, when the current in the region over there, and the region that we had for amplification, depends only on VGS. It was not a function of VDS anymore. Now, if you increase VCE even further, you end up, it causes breakdown in the transistor, and the transistor can overheat. We usually work below this VCE max. We shouldn't allow the voltage across the transistor to exceed a certain maximum value. So the first one, as we agreed, the first region, this is called saturation region, where the VCE is small. The second one, when VCE is greater than 0.7 to VCE max, the collector base junction is reverse biased, base emitter junction is forward biased. The current does not depend that much on the VCE, it depends only on the base current. And this is how we use it as an amplifier, by making very tiny changes to IB, the base current, and because of the high gain, this will cause large changes in VCE, and then you see very large fluctuations of voltage at the collector. So this is how this is used as an amplifier. It's called the active region. Of course, the third region of operation is a breakdown. When you exceed VCE max, this will cause strong change in current. We usually don't operate in this region. The last one is when the base current is zero. The base emitter junction is not forward biased. So the voltage you apply between the base emitter is not sufficient to turn on, to forward bias the base emitter junction. In that case, the base current will be zero and the collector current will be very small. And we said that the transistor in this case, the cutoff region, and the transistor in this case represents an open switch. So the transistor, either if you use it as a digital switch, it alternates between the cutoff region when there is no current and the linear region when there is very little drop across VCE. It represents like a very small resistance. Okay, for this one we want to draw the family of curves for the shown transistor if beta DC is equal to 100. And the IB is varying from 5 microampere to 25 microampere. Very simple. In the active region of operation, the characteristic is horizontal. You multiply this 100 by the value of IB. And when the voltage VCE drops below 0.7, you simply draw a line, and this line will represent your saturation region, where there is an ohmic, it's an ohmic-like region. The transistor really represents a very tiny resistance. So this is what you have here. If your base current is 5 microampere multiplied by 100 in the active region, then the corresponding collector current will be 0.5 milliampere. Up to when VCE reaches 0.7. If VCE drops below 0.7, you enter the saturation region. And you can see there's a line connected to the origin. When IB is equal to 10 microampere, then in the forward active region or the active mode of operation, you will see that the characteristics will be horizontal, and the collector current is equal to the base current multiplied by 100. So 10 microampere by 100 will give you 1 milliampere, okay? But once the voltage of the VCE reaches 0.7, you can simply draw a line connecting this point to the origin, because this is the ohmic region or the saturation region. The same thing is happening here. 15 microampere will give you 1.5 milliampere here. Of course, this 1 milliampere for the collector. And once you reach 0.7, you get a linear line here in this case, which is showing that the transistor really is in the saturation region. So this is the active region, this is the saturation region. Of course, if I base is equal to 0, the collector, this will be given as this line here, the collector current will be equal to 0.